Hey guys, so today we're going to continue with the material we covered on Monday. We're going to start off by reviewing correlation. I feel like there was a lot of material there, and I think going over it a second time will be really helpful. Also, I missed a couple caveats that are really important regarding correlation, so I'm going to cover those now. And then we're going to get into more detail about linear regression. It's not going to be super thorough, just a high-level overview, but more than we got to last class, and that'll be helpful in some of the intuition behind the coefficient of determination. And lastly, we're going to have a really quick review of what we covered in terms of bivariate analysis when one or more of your variables are categorical. So let's start by reviewing variance and covariance. So here we have the formula for the variance of x, right? And you might remember when I first introduced standard deviation, this was the formula just wrapped in a square root. So the variance is very similar, you've just squared it. The covariance formula is very similar to the variance formula. The main difference is you're multiplying every deviation in x with the associated deviation in y, and then summing them up. Whereas here you're multiplying the deviation in x with itself and then summing it up. So they're very similar. In fact, I could write this in the same format as below if I just replace the y's with x's and the y bar with an x bar. I know this is different than how you've seen variance in the past, especially these subscripts over here, where I have x with itself and then x with y. But I want to introduce this new notation, even though mathematical notation can be a little intimidating, because it's going to be really helpful in our discussions, specifically about correlation, and later when we get to regression at the end of this lecture. So yeah, sorry to deviate from what we initially went over, where variance was just s squared. Now we have this like double x over here, and this x and y. But it's going to be, if you can get used to this new notation, it's going to serve you really well through the rest of this lecture and hopefully future content. Okay, so here's the correlation coefficient, and here you see that notation that I just introduced. We're talking about the covariance between x and y, which is itself a measure of how x and y vary together, but it's not standardized, and it's hard to interpret because it depends on the units of x and the units of y. So here in the denominator, we just take the square root of the variance of x multiplied by the variance of y, and that normalizes it so that it's between -1 and 1, and it's interpretable regardless of the data I'm looking at. The interpretation remains the same. Last time I showed you this, there was another right-hand side with the population correlation, and that was with the Greek letter rho. It's exactly the same formula though, just with a sigma replacing the s's. And this time I intentionally didn't include it because there's no need to confuse you with that information. The vast majority of the time we are dealing with sample data, right? That's what statisticians do. We deal with the sample and use that to make inferences about the larger population. So you do still have two formulas here, but they're identical. This one is just a simplified version of this formula, because when you take the square root of the variance of x, what do you get? Nothing but the standard deviation of x. When you take the square root of the variance of y, what do you get? Nothing but the standard deviation of y. So you could think of it either way. Sorry about that, bounced around. But I do find it helpful to think of it in this format, but whatever makes it easier for you. So these are the two caveats I missed last class that I want to cover really quickly. So correlation specifically measures the linear relationship between your variables, meaning if you were to draw a line through the variables, how accurate is that representation of that data? And as you can see in this data, let's ignore the line in these charts for a second, but in this data, X and Y clearly are related, right? I see that in this range, as Y increases, X decreases, then in this range, as Y increases, X increases, so forth and so on. Same thing here, right? These data vary together. Knowing something about X tells me something about Y. There's a relationship here. It's just not exactly linear. This is piecewise linear, as in this half of the data could be fit well with a line. This half of the data could be fit well with a different line, with a different slope and a different intercept. But a single line, as you can see, if you try to fit it through the data, doesn't do a great job. Its slope is pretty close to zero. Same thing here. And so what you see in these legends in the bottom is the initial correlation coefficient. So before any transformation, which is something we're not going to cover in this class, but before manipulating the data in any way, our correlation indicates that there's no linear relationship, right? These values are close to zero. Here we have somewhat of a decent linear relationship, but it's actually understated because of what I mentioned before regarding the piecewise linear nature of this scatter plot. So if you transform it, you actually see it's a stronger relationship than we intended. Again, we're not going to cover transformations in this class. The real point of this picture is just to show you that the correlation coefficient that we're studying, little r, measures linear relationships. It doesn't, so when it's zero, that doesn't mean that the data aren't related. As you can see in these two cases, the data are clearly related. However, it's not a linear relationship, and so we get a very low value, near zero, for the correlation coefficient. The other caveat that I wanted to go over, and you've probably heard this many times, but correlation is not causation, right? It tells us that the two variables are related, and even in that example we had last class about wine and heart health, I was able to make up a story that explained another variable that was actually influencing both wine consumption and heart health. That may or may not be true, but it's just one example of how variables can be related, but not necessarily causally related. And what I mean when I say causally related is one variable is having a direct effect on the other variable. And this is just a funny comic off XKCD, kind of making that point that just because two things tend to occur together doesn't mean that one explains the other. Now, obviously, this comic is being a little facetious. The statistics class obviously did have the effect of explaining causation to him, but he's taking it very seriously and, remarking that he's unsure. But yeah, I think as statisticians, it's always important to keep that caveat in mind, right? These things vary together. One might be helpful in predicting the other, and vice versa, but that doesn't necessarily mean there's a causal effect. If this happens, then this will happen to the other variable. Okay, so now let's get into regression, which we talked about very, very briefly last class. We're still going to be brief about it here. We're not going to go into a ton of detail. I know there's a ton of mathematical notation on this slide, which can be intimidating, but bear with me. We're going to go through it one bit at a time, and it will make sense. So regression, I put linear in parentheses. Sometimes you'll hear it referred to as linear regression, also known as least squares or ordinary least squares. Why is it called least squares? Well, because the way you solve for the regression line, which is what you see here in red, is by minimizing this quantity. So you're actually summing up, there should be a sum symbol here, sorry, I forgot to put that. You're summing up the difference between your predicted values, y hat, which is all the points on the red line, and your actual values, y, which are all your individual points, right? So here at 40, right, my actual value is around 30, and my predicted value is around, 25, right? So that's going to give me an error, also known as a residual, of 5. and then we square that and we try to minimize the quantity of all those square residuals summed up. You don't actually need to do that. You can derive it mathematically if you wanted to, but we're not going to cover that in this class. I just want you to be aware of how these regression equations, which we're going to go over in a little bit, are derived. It's by minimizing the sum of the errors, the sum of the square errors, which is why it's sometimes referred to as least squares regression, and ordinary because there's other ways to go about it that we're not going to cover in this class. But if you take more advanced classes, you will learn about other ways to treat those errors. Now, I wrote those errors as y minus y hat here because y hat, again, is the predicted value and y is the actual value. You could also write them as epsilon. So these two equations seem very similar, right? But there is a difference. And you probably notice one of the differences is epsilon. The other difference is that this y has a hat, right? So if I do y minus y hat, right, the beta 0 is going to cancel with the beta 0, the beta 1x is going to cancel with the beta 1x, and all I'm left with is epsilon, the error, how much my actual data point was from my predicted data point. That's the error. And there are some assumptions associated with that error, which we will get into. I'm thinking what I'm going to do is I'm going to make it optional, assuming our pace continues, the course continues at a good pace. I'm going to optionally go into more detail about regression for those of you who are interested, because it is a really powerful tool for making predictions. For now, though, I just want you to be aware that this is kind of the underlying model that we impose as statisticians in order to build a regression model. The underlying reality that we're assuming underlies the data in order to build a regression model. So what does this mean? What probably looks familiar to you. Let's ignore the epsilon for a second. This looks a lot like y equals a plus bx, right? Just the a is referred to as beta 0. It's just the convention in statistics for the intercept. We don't call it a anymore. We call it beta 0. And the b is now called beta 1. And there is a reason for that, and you'll learn as you get into more advanced statistics. But for now, just know that instead of saying y equals a plus bx, we say y equals beta 0 plus beta 1x, and we mean exactly the same thing. Y equals some intercept, whatever you want to call it, a or beta 0, plus some slope, b or beta 1, times x. But there is this other term, which is the error, right? Which is just telling us, here's our y hat right here. This is what we predict. And it's not always going to be accurate. Sometimes it might be. We could have an error of 0, as in this case, where the point lies directly on top of its prediction, as in all those cases. But sometimes there's going to be some noise, which we call epsilon, or error. You could refer to it either way, which is just the distance between the actual and the predicted. So this is kind of the model we're assuming our data follows. And then in doing so, we do some calculus to minimize the errors squared, the sum of the errors squared. Sorry, I missed that in this slide. I will fix that later. And when you do that, these are the equations you get for beta 1 and beta 0. Sorry, sometimes this jumps around. So what do these mean? Well, the equation for beta 1, at least the numerator, is exactly the same as our equation for our correlation coefficient. We're looking at the covariance between x and y. How do they vary together? The difference is really in the denominator. And again, we have the variance of x, but we no longer have the variance of y, and we no longer have the square root. So this is a simpler equation to get at the slope, also known as beta 1, of our regression equation. Then to get the intercept once you have the slope is pretty trivial. You take the mean of y minus the slope, which you had previously found here, times the mean of x. And that's how you get the intercept. You can derive this all using calculus like I mentioned before. We're not going to cover that in this class. You You can take my word for it. You can try to derive it. But these are the equations to solve the regression line, which we write like this. Y hat, our predicted value, equals some intercept plus some slope times the value of x. So let's do a quick example. So this is actually a question that I borrowed from your homework. You're going to do this week. We're looking at the relationship between hits and runs. And as you can see, they seem to be associated, right? The data does follow a line. There is some noise or error, right? It doesn't fall exactly on the line. But the line seems to be a decent approximation. And when you do this in your homework, you will see the error bars associated with the line, which I think are important because it kind of tells you the potential range for the slope and intercept. And you'll see that it's a pretty narrow range. And we can make some assumptions about what that slope and intercept might look like. But this is just our measure of center. So here I'm violating one of the principles that I told you in our very first class, which is to always include or to quantify uncertainty when you're reporting out your metrics. This is just for illustration, however. The true intercept could be slightly larger, slightly smaller, quite a bit larger, quite a bit smaller than 3.809. The true slope could vary from 0.535. But in this case, we're just reporting our best guess. And I do think it would have been better to include the range on what those values could be. But you'll do that when you do your homework, you'll see that. So using this regression line, which again is derived from the formulas on the previous slide, right? So our beta 1, our 0.535 came from the covariance of x and y divided by the variance of x. And then our beta 0 came from this relatively simple formula. Once we have the slope anyway. So let's practice. I want you to think right now. Please estimate. Don't spend a lot of time being exact. Just a rough estimate is fine. How many runs would you expect from a player who had 100 hits? So there's a few ways you might have approached this problem. First, you could just look on the graph and say, well, 100 hits is right here. If I go up, I have one data point here, one data point here, a prediction over here. The prediction seems to be around 52. The points are a little higher, so maybe I want to not trust the regression line as much and take the mean of those 2 points, around 60. And all of those are fine answers. But what most people will do in practice, and we'll cover this towards the end of the class, time permitting, is they'll plug 100 into their regression line equation. So 0.535 times 100 is just 53.5, right? Because I'm moving the decimal over twice. Let's round and say 54 to make it easy. Plus I'm adding about 4, so I get 58, which is a pretty close approximation to what I got when I just looked at the line and when I looked at the 2 dots. So that's kind of how you would use your regression line to make predictions. Again, I am violating that rule about quantifying uncertainty. You should always include some kind of bounds, a lower bound and an upper bound for where that might live. But our best guess is about 58, and that's rounded. So you could come up with a more accurate measure of center by not rounding. All right, so now let's go back to the coefficient of determination. So this is all information you knew from last class, right? You knew that the coefficient of determination, known as r squared, capital R squared, is equal to your correlation coefficient squared. So the correlation coefficient we mentioned lives between -1 and 1, where the sign tells you the direction of the relationship. Negative would go down from left to right and positive would go up from left to right. And then the magnitude, meaning its distance from 0, tells you the strength of that relationship. That's all stuff we covered in last class. On the other hand, the coefficient of determination, r squared, capital R, lives between 0 and 1, which makes perfect sense because if you square something between -1 and 1, you're going to get something that lives between 0 and 1. So the interpretation is similar in terms of magnitude, but you no longer get the direction of that relationship. Now, how do you interpret the coefficient of determination? So I didn't mention this last class, but I want you to be aware. The idea behind it is what, and it's often given as a percentage, but you can write it as a decimal. But when it's given as a percentage, the idea behind R squared, capital R squared, I want to be clear, is the amount of variation in y that is explained by your independent variable x. That's the interpretation behind R squared. Using regression, there are other ways to derive R squared besides the coefficient of determination, besides the correlation coefficient squared. Again, if we cover that, it'll be at the end of the class as extra material for those of you who are interested. It's not something that's in the scope of this course. Sorry, that was a repetitive slide. I will fix that. Oops. Okay, so a quick example of interpreting R squared. So here's my correlation coefficient of this data. As we expect, no surprise, it's positive. I can see, right, this line, this scatter plot, even if I ignore the line, trends upwards. It's also really close to 1, which I kind of expected because, most of the points are close to the line. It follows a pretty clear linear relationship, especially in this earlier half. There is an issue with the fact that it's tighter here than here. But again, that's something we'll cover towards the end of the course, time permitting. So the correlation coefficient is interpreted exactly the way we would expect. It's positive. It's pretty close to 1, indicating a strong relationship. So if I want to get the coefficient of determination, I just square it. And if you do in a calculator 0.9177 squared, you will get 0.8421 squared. So again, let's interpret that. What does that coefficient of determination, R squared, tell you about the relationship between hits and runs? So hopefully you remember from the last slide, that's telling us that approximately 84.2% of the variation in runs is explained by hits. There's still quite a bit of variation that's not explained, which is evident. You see points that don't lie directly on the line. That those are errors, sometimes referred to as noise. But a good chunk of the variation in runs can be explained by hits. If I know the hits, I can give you a pretty good idea of the number of runs. This is the really high value for R squared. You rarely see things this high in practice. But this does kind of make sense because intuitively, even if you don't know much about baseball, the more you hit the ball, the more likely you are to score runs, right? That's just how the game works. All right, so we talked a lot just now about the relationship between two quantitative variables. I'm going to very briefly go over the relationship when you have two categorical variables and then when you have a categorical variable and a quantitative variable. And we did cover this material earlier, at least as far as visual representations of that data, and we will hint at future analyses we'll do when we start to get into inference for these kind of bivariate relationships. All right, so let's start with the relationship between two categorical variables. So as we had mentioned in previous classes, visually, you have a lot of choices. The two-way table, which is also called the contingency table, or side-by-side charts, which you do in your homework. Pie, donut, bar charts are all appropriate for categorical data. Inferentially, we haven't talked about this, but there is a test of independence known as the chi-square test, which just examines if a relationship exists between these two variables, and we will cover that later this semester. On the other hand, when you have a categorical data that you believe, remember statistics doesn't tell you this, but you make the assumption when you label it as independent or dependent, is influencing the outcome, which is quantitative, inferentially, instead of a chi-square test, it's now referred to as a t-test or an ANOVA. And both of those are very closely related to regression. In fact, ANOVA is a form of regression. The main difference is that your explanatory variable, also known as your independent variable, is categorical. And then visually, we talked about you could have side-by-side box plots, histograms, or density plots. We also talked about violin plots briefly, which is another option, but I think if you're going to do a violin plot, might as well just do a density plot. Although they can be helpful if you have a lot of categories and you want to see them side by side. Okay, so that's a little bit about the relationships between those variables. I know we spent a lot of time on the quantitative and the quantitative bivariate analysis. That's because there's more techniques that are appropriate to introduce at this time. But we will get into those other inferential tests in the future. I realize the material is getting somewhat more advanced, especially for people who might be intimidated by mathematical notation or math more generally. So please reach out if you have questions via email if you're more comfortable with that, or via office hours, however you prefer. It might seem like a lot, but this information is really closely connected. So you might have noticed even in this lecture, right, the formula for correlation and the formula for beta 1 have the same numerator, right? And the relationship between the coefficient of determination and the correlation coefficient is pretty clear. And similarly, you can make another relationship using regression, which we didn't cover. But the concepts are all closely related, and I want you to kind of connect those concepts as you're learning them, which will be easier if you ask questions, because then I'll be able to reinforce those connections. So it's not quite the same as just memorizing a ton of information. The more connections you make, the easier it'll be to remember that information. So yeah, this is kind of the elbow point in the class where things will ramp up and get more mathematical. And I do want you to please ask questions. So I just wanted to emphasize that again. It'll be very helpful for you, for me, and for your peers. Thank you.